Before I still get into arc length, I'm going to go ahead and just kind of develop the concept a little bit more. And so, one of the things that I need to talk about real quickly is just vocabulary. So, for instance, in this case, I need to talk about what a rectifiable curve is. So, a rectifiable curve happens to be a curve or some kind of graph, a function that is continuously differentiable. What that means, hopefully, you guys already know a little bit about it, was that it has to be, number one, continuous, and number two, has to be differentiable over the entire interval that we're looking for. So it doesn't have to be continuous or differentiable everywhere, but it needs to be continuous and differentiable on the interval that we're looking at. So one of the other ways we can describe this, hopefully you guys can think about it, would be we would describe it as a smooth curve. Okay, it's another way to describe it. So again, let me repeat. We're talking about continuously differentiable curve on an interval. So no jagged pointy spots, nothing like the absolute values where it bounces off. So it needs to, again, just be a nice, pretty smooth curve. So what I'm going to do is I'm going to take this idea, this rectifiable curve, and I'm going to use it in example 3 to estimate the arc length of y equals negative x squared plus 4x plus 1 between the values of 1 and 3 for x's. Now, I want to point out to you, I went ahead and graphed it because graphing it is always going to be very, very helpful when you're talking about this stuff. So notice I've got an x value of 1 that I plugged in. I've got an x value of 3 that I plugged in. The y values that I got are up here, okay? And so I went ahead and graphed it, and I also made myself a nice little table of values because I am not actually going to find the exact arc length. I'm just going to try to estimate it to the best of my ability. Now, one of the other things that I wanted to point out to you, in example 1, we were trying to find the distance, between the points 1, 4, and 3, 4. Notice right now, I've actually got a curve that goes through and ends at 1, 4, and 3, 4. And so what that distance was, and I'll grab this red marker, was this straight line connecting them, okay? But here's the thing. In this case, let me get to it, is I'm not talking about a straight line. I'm no longer talking about a geodesic, the shortest length path between them. I'm talking about a curve that connects those 2 points. And hopefully you guys are realizing that, again, that geodesic, that red little dotted line right here, is the shortest one. So this blue one obviously has to be longer. It has to be more than, again, example 1, we found the answer was 2. It has to be more than 2. So the question is, let's try to estimate it. Let's try to see how well we can estimate it. So what I'm going to do first is use n equals 2 regular subintervals. That means I'm going to essentially cut this function in half and try to estimate it that way. So here's what I'm going to do. I'm going to estimate the distance, or this arc length. I'm going to estimate the arc length using the distance between those 2 points, the halfway mark at 2, 5, and the distance here. And notice that's going to be a better estimate than if I just said the answer was 2 for the red line. In this case, I'm using these little purple dotted lines to, again, help me estimate a little bit better what that arc length would be. So here's what we're going to do. I'm going to calculate the distance between these 2 points. Then I'm going to calculate the distance between these 2 points, and I'm going to add them up. So 1 to 4, or 1, 4, 2, 5, and 2, 5, 3, 4. I'm going to calculate those distances real fast. It's not going to take me very long. They're not that far apart. Notice 1 to 1. So it's going right 1 and up 1. So I'm just going to do the square root of 1 squared plus 1 squared. Let me repeat what I'm writing down. If I'm doing this in my head, we're going to do 2 minus 1 squared plus 5 minus 4 squared. And essentially, that's going to eventually give me the square root of 2. So that's the first part. That's the distance there. I'm also going to go ahead and, again, calculate 2, 5 to 3, 4. So if I do this one, I'm going to do 3 minus 2 squared plus, in this case, I'm going to do, since I did 3 first, I'm going to do 4 minus 5 squared. Again, I'm still going to end up doing the same thing. 3 minus 2 is 1. 4 minus 5 is actually going to be negative 1. When you square it, it still becomes positive. So I'm going to end up also with the square root of 2. So when I add the square root of 2 plus the square root of 2, it's going to give me 2 square roots of 2, which I don't know what the answer off the top of my head is. Let's see what I get. 2 square roots of 2 is approximately 2.828, and I'll leave it at that. So right now, that's my current estimate. So notice we started off with 2. That's how far it is from this point to this point. Now that I've added this extra, I'm going to call it dimension, this extra little bit of a curve here up to 2, 5, now I've got a little bit of a better estimate at 2.828. So what I'm going to do now is I'm going to go a little bit further. I'm going to go from n equals 4 regular subintervals. So notice I went ahead and wrote all of my table of values down, so it made my life a little easier. Because what I'm going to actually do, instead of doing the whole number ones, I'm going to do half number ones too. So I'm going to include 1.5, 2.5. And so if I grab another color marker, let me do that real fast. I'm going to choose, let's do this green marker. What I'm going to do is I'm going to, again, red line was the geodesic. This kind of purplish pinkish line that I wrote here was n equals 2. What I'm going to do is I'm going to start here. I'm going to go up to this other dot right here, which is at 1.5, 4.75. I'm going to use that to go to the next dot. Hopefully you guys see that I'm subdividing the curve a little bit and just calculating straight line distance between those points. So like I said, I'm going to go from this one to this one. I'm going to go from that one to that one and keep going. Now notice, hopefully this makes your life easier. It is a little bit symmetric, so if I find these first two, the second two are going to be the same. So I'm going to kind of erase this a little bit. I'm going to rewrite my math a little bit and just try to calculate it out real fast. So in this case, I'm going to do 1.5 minus 1 squared plus 4.75 minus 4 squared. And we'll see what happens when I do that. So square root of 1.5 minus 1 is 0.5, excuse me. I'm going to square it, and then I'm going to add 0.75 squared to it. And I end up with getting the square root of 13 over 4 as its answer for in between those 2 points. I'm also going to go again from 1.5 to 2. So I'll use 2 minus 1.5 squared plus, this is going to be 5 minus 4.75 squared. All right, so I'm still going to end up doing 2 minus 1.5, which is 0.5 squared, but this time instead of having 0.75 squared, this is 5 minus 4.75 is 0.25. So I end up getting the square root of 5 over 4. So that's nice. That's this distance again from 1.5, comma 4.75 to 2, comma 5. Let me repeat again. It's going to end up being the same thing because this is a nice symmetric graph. You can calculate it just to be sure. 2.5 minus 2, 4.75 minus 5, 3 minus 2.5, 4 minus 4.75. You're going to end up getting the same answers, just this one's between here and the square root of 13 over 4 is here. So all I'm going to do is double them, or I'll write them over here. So I'm going to have, again, the first one is the square root of 13 over 4 plus the square root of 5 over 4. Then I'm going to do it again. Square root of 5 over 4 plus the square root of 13 over 4. All right. Once I do all this math, it should end up nice and pretty for me. So square root of 13 over 4 plus square root of 5 over 4 plus the square root of 5 over 4 plus square root of 13 over 4 gave me the square root of 13 plus the square root of 5 over 2, which is approximately 2.92 and a bunch of other stuff over at the end, but it's 2.920, so I'm just going to leave it like that for now. But that's the important thing that I wanted to point out to you again. I'm getting closer to an actual estimate. So at this point, I'm probably going to guess that we're approaching towards 3, and that's probably a decent guess. It's not going to be exact, but it's pretty close. But so that's essentially what we're doing is we're subdividing this curve into smaller and smaller places, and we're finding the distance between them. Hopefully this sounds pretty reminiscent to you because we're getting into integrals. We're talking more about integrals, and that's what I'm going to do in the next video. So hopefully this helps you guys understand how to estimate, just again, using table of values and using this method. Again, we're calculating distance between points. So coming back in the next video, talking more about arc length.